So, good afternoon. We start again with our remote seminar a bit later today. Our speaker is Eros Vanzella from the observatory in Bologna. I'm very happy to introduce him because I know him since a couple of decades, since we met at the Astroamateur Observatory in our hometown. And it was clearly since then, and it was way, way, way better in doing observations, even if that was like, I don't know, a 40 centimeters telescope. Then, coming to his career, Eros took the PhD at ISO in Garki in 2003 and then moved in Trieste for postdocs for 8 years. And since 2012, he's a researcher at the INAF Observatory in Bologna. And he will tell us today about exploring the very high redshift universe with cosmic telescopes, so lensing. Please.
Okay, thank you, Franco, for the introduction. I'm sorry I was a bit late today. Yes, today I would like to show you some initial results from a project that we are starting to work in that is on lens fields, and I will also focus on an exceptional object that is a sort of super lens that is telling us a lot of things, a sort of laboratory. So whatever I'm going to show you is based on a lot of effort with the help of many people that are listed in the bottom of the slide. So let's start with some motivation. The first is cosmic hydrogen reionization. That is, just in few words, let's say a combination of three main factors. One is the star formation rate of the universe. This is the sigma star formation rate density of the universe. This is the CI, is the ionizing photon production efficiency that is related to the nature of stellar populations that are involved in this process, that are producing ionizing photons. And this is the fraction of photons that actually escape from these high redshift galaxies and ionize the entire universe. So this is a quite complex problem that is connecting several things, starting from the star formation rate, the global star formation rate, the stellar populations, and also the status of the interstellar medium and the transparency of the medium. And actually, recently people are looking for very faint objects that maybe are playing a dominant role in the production of these ionizing photons. And when we are looking for very faint sources, actually we are entering in a regime that is something like more close to a star-forming complex or even star clusters. And this, I think, the time is mature to search for stellar clusters even at high redshift. And I will show you some possible examples. We are really at the beginning. So the two things are connected, in my opinion. So just say a few things about as an introduction. When we are looking in the field, that is non-lens field, not non-magnified fields, and we take, for example, one of the most deepest, that is the Hubble ultra deep field. So we have something like objects that are detected down to magnitude 29 or 30, but with a signature noise that is quite low. And moreover, one HST pixel that is typically 30 milliarc second is probing 0.2, 0.3 kiloparsec physical at redshift 2 up to 7, more or less. So here is a sort of cartoon. You have one inside a single pixel. We know that there is a lot of things, okay? There are a lot of things. There are OB associations, star clusters, H2 regions, and so on. This is an example with a scale of 90 parsec. Physical, of course, obtained from the ground, from local universe. With strong lensing, actually, we can gain in signal to noise and also spatial resolution. And when we couple strong lensing plus HST, we can do a nice job going down to 50, 100 parsec scales. When we will combine strong lensing and super AO facilities like ELT or MEVIS, then we can go down to a few parsec scale, even at high redshift. So we started with a program some years ago, actually. It was a bit slow in this execution, but this is, we call the MUSE deep lens field. We asked for 20 hours, we got 17 hours integration time in a single pointing in one of the best cosmic telescopes, that is the MAX J0416. And this is the layout of the MUSE deep field. This is another MUSE pointing available. And yes, so this is 17 hours integration on a single pointing. This is the list of the COI. And there are 2 papers in preparation. One is on the presentation of the project, and the other one is on the construction of the lensing model of the galaxy cluster that I will show in a second, some features. Of course, MUSE is an integral field spectrograph, very important, and for at least 3 reasons. The first is that there is no target preselection, so whatever is in the field of view of MUSE above a certain flux threshold is captured, and therefore you can get spectroscopy immediately for whatever you are in the field, of course, if there is emission lines or the signal is high enough. This is an example of an object, let's say, with the lemon alpha emission. This is the HST counterpart of magnitude 29.5, and when you delens this magnitude, you go very faint, no, down to 31.3. In this way, we can confirm objects that are extremely faint, that was not possible with slit, with the all-style slit spectroscopy. It was not easy to ask for hours to look for an object with this kind of magnitude. Okay, with MUSE, by definition, these things are included. The second point is that since it is an integral field spectrograph, we are covering also the caustics, and so we can probe extremely magnified objects. I will show you some this particular case we discovered in a few minutes. And third, we can really capture multiple images produced by strong lensing in a single shot, very faint. So here is a sort of a history on this for this galaxy cluster, where people used different systems, a number of systems to constrain lens models, starting from Grillo 2015. This is 8 systems that produce typically 3 times multiple images, so 24. This is from GLASS, this is from MUSE Caminha 2017, and this is from the MUSE deep field we have. So we have now 66 families and 182 multiple images. That is quite impressive, and this is the first time that we have this kind of this very, very large number. And the model must reproduce exactly the position of these multiple images, and actually we are obtaining an RMS that is 0.42 arcsecond. So it's very important to have a very precise lens model for this kind of things, because we want to lens and obtain information from the physical properties. So this is just to show you what is the equivalent if there is no lensing, actually. In other words, which kind of integration time you need to obtain the same signal to noise we are obtaining with our MUSE deep field. And here you see the contours of ours. So in practice, the entire field of view is probing an exposure time that is more than 100 hours without lensing. Okay, this is not very new, but with a deep field, actually, we are gaining a lot, even where the magnification is relatively low. Of course, lensing is decreasing a lot the volume probed, the effective area that is probed, and this is the cumulative surface area versus mu. And here you see how this area is going down rapidly. So from one point of view, we can probe very faint objects and very small scales, but we are probing much smaller area, of course. So this is another just color to show this MUSE deep lens field, and this is the layout. And there are a lot of systems that I'm going to show you some examples in the next 2 minutes. And this is just to show a magnification map at redshift 6. This is where you see white region is where magnification is increasing. And the critical line actually is on the top of this. This is at redshift 6. Let's show you 3 examples. This is one example. At redshift, it's not very high redshift. This is 1.9. And here is the image of a group of a galaxy, let's say. And on the other side, there is the other version of the same galaxy. And here you see all the features that emerge thanks to lensing, and like these tiny nodes, star-forming nodes. And this is the critical line. So whatever you have in this side is mirrored to the other side. And of course, with MUSE, you can also look at spectroscopic features emerging from single clumps. Another example is this one. There are 2 multiple images of the same system, and here is the system. the 20i and 20b, and you see by eye that this image is in practice the same as this one. And what I would like to emphasize here is that if you want to focus on these tiny star-forming regions, actually, the mirroring introduced by lensing is very important, because you can confirm notes that maybe for that you don't have spectroscopic confirmation, but because of mirroring, you are pretty sure that this is part of the same system, like this knot that is redder than the rest. Imagine that you have only one image, and it's not so trivial to associate one knot to the rest if you don't have redshift. But in this case, actually, we are quite sure that it is part of the same system. So it's very nice, because you can start studying performancity fitting, or study physical properties of these knots individually at the scale, let's say, between 60 and 300 parsec. This is the same image in the F814, and this is Lemon Alpha from MUSE. And here is the knot, the red knot, and actually, in fact, from the set fitting, you see that this is red than the rest. This is this core is this set fitting here, just to show you that what I was saying before. And the third example is another one at redshift 5.1. Here is the image on the one side of the cluster. This is the less magnified image. The observed magnitude is 28.3, and the intrinsic one is 29.16. But in the other side, you have the version, the magnified version, and you see that features emerge again. And here there is the three main features that are mirrored again respect to the critical line. And if you go to the detail, then you can start looking at the Lemon Alpha emission that is not aligned with the main, let's say, body of the galaxy, but is apparently emerging from the fainter nodes here. And maybe also this one is the size is probably less than 40 parsec, and this is the absolute magnitude, and the stellar mass will be very small, just converting the ultraviolet absolute magnitude we have. So okay, there were three examples, but at the end there are 182 multiple images, 66 families that are split over 116 individual clumps, and here are all images, and just of course you can't see details of those, but for each of them we also start to look at the details, like this extracting the relevant features, like from MUSE. This is Lyman alpha, this is carbon 4 nebular emission, helium 2, oxygen 3, carbon 3. Okay, and for those you can play with magnification, redshift, absolute magnitude. These are the parsec probe for each pixel, stellar mass, and star formation rate. This is very at the big. It's still preliminary, but we are building a sample of something that is quite interesting. And this is summarizing what I was saying. This is a plot showing you the size versus absolute magnitude. Color code as the lens magnitude. So okay, this is the intrinsic magnitude, and this is the size of the symbols is marking the redshift. So starting from what we have in the field, like good south, where there is no magnification, these are a sample that is coming from our previous work. And here there is this cloud that is what I was saying before, this coming from the MUSE deep lens field, and we are starting to probe really clumps, very faint objects, and small objects, actually. This is the magnitude distribution, and you see that we are probing things that are fainter than magnitude 30, up to 32, or maybe even up to 35. And this is the Lyman alpha fluxes that we are exploring. So very faint objects. And maybe, yeah, we are moving from galaxies to clumps, and maybe at this regime, when we are touching a size like 10 parsec or even smaller, then we are probing single star clusters.
Sorry, Eros, I think we have a question for you right now from Angela Bragaglia. There is, may I ask if the narrow field mode of MUSE would help getting more details?
Yes, but currently the narrow field mode is not is very difficult to provide a target, because you need a bright star within 3.35 arc seconds from your target. Bright star means magnitude brighter than 13, 14, something like that. So it's very difficult to have this kind of bright star for AO correction. Even though we got time for another target that I have not time to show you here.
Okay, I think it's okay.
So, so yeah, this is the same plot. I'm like to show you some details here. Okay, this is a system that we already published in 2019 that is the same here, where the core of this galaxy, we estimate a size less than 13 parsec. Another one is very promising, is possibly really, we have to work on that, but might be we can assess if it is gravitationally bound or not, and the size is extremely small. Another one is very compact. This is another galaxy that is crossing the critical line. You see all the knots here are mirrored in the other side, and the magnification for this knot is very high. And so I think that this is extreme, and the size we got is something like 5 parsec or something like that. So these are really, at least these two systems, 1 and 2, probably we can say if they are gravitationally bound, calculating the dynamical age. Okay, so I would like to show you now in another extreme case we found that is crossing the critical line at redshift 6.6. And this is an arc, a very small arc that we see emerging. This is the lemon alpha observed. This is the magnitude that is basically not detected from HST, even combining Y, J, JH, and H. So down to, let's say, 31 magnitude 2 sigma. So we performed simulation, simulating the caustic crossing performed by Massimo. And actually, we reproduce quite well what we are observing with the model. And just to make the story short, the point is we are observing two multiple images that are so close to the critical line that they are merging all together. The third one is on the other side of the cluster. Okay, so the MUSE dip is important in this case, also in this case, for two reasons. The first is that we detect the lemon alpha at syntenoid 17, so we see the symmetry of the line. And the second point, maybe this is the technicalities. I will jump here, but the end of this part is that the magnification is relatively robust, above 40. So this would be the faintest lemon alpha emitter ever observed close to the ionization epoch. And moreover, the equivalent width of a lemon alpha line is extremely large, is plausibly above 1000 Armstrong rest frame that will open for candidate POP3 stellar complex at this redshift. And here, maybe this is an ideal target for DLT or even JWST. We are really at the limit of the current facilities. Let me move to the second, yes, just to the last 5 minutes, showing you another extreme example that is super magnified. And this is the case of the sunburst arc that we are working on also on this system. And here the situation is a bit different because magnification is enormous. And for an object that is not extremely faint, so we are observing interesting details on this. Here is a summary of the arcs. There are 1, 2, 3, and 4 arcs. And looking carefully at all the features, we identify all the multiple images and mirroring introduced by lensing. And again, there are a lot of details, but if you focus on the knot AA, so the knot A is replicated 12 times. And from the knot A, Rivera Thorsen 2018, this is a science paper, detected Lyman continuum escaping. So ionizing photons escape from this knot, perforate the galaxy, and reach the observer. There are other interesting features on this arc that we are going to characterize in the future. And just to show you in a second these features, this is a zoom of the arc number 1. So this is a knot A again, A. But there are a lot of tiny things, okay, that are replicate respect to the critical lines that are marked here with yellow dashed line. Consider that 1 pixel along the arc is probing 5-10 parsec. So this is impressive in terms of search for star clusters at this redshift. The arc number 2 shows similar things, again, the same features. And again, there's a lot of information contained here. That focus on the knot A, this is a MUSE spectrum. And you know, there is, because of the magnification, syntenoid is impressive, and we see very nice features like U with Piscini profile of the carbon-4, broad helium-2 emission, oxygen-3 nebular emission, and so silicon-3, carbon-3. And if we compare this spectrum with spectra obtained from local star clusters, here I'm reporting some from Laterer, Smith, Crowther, this famous R136, and this is our knot A, and this is a redshift 2.4, okay? This is a cosmological distance. The other three are at megaparsec distance.
20 minutes.
Okay, so this knot A has an age estimated of about 2.9 mega year by Chilson et al. 2019, based on these Starbars 99 or BPAS models, and mainly from this Piscini profile of the nitrogen 5. This is a good indicator of the age. We got executor time of this knot A. This is just preliminary. This is, I think, 800 seconds. Again, you see very nicely a lot of features. There are tons of features that we have to explain. But what is nice is that since it is a Lyman continuum emitter, so ionizing photons are escaping, means that the column density of natural gas along the line of sight is smaller than 10 to the 17.2. Okay, and indeed, in the Lyman alpha line profile, this feature is very nice captured because of this peak of Lyman alpha emission at the systemic redshift. So it is telling us there is a route, optically thin route, where Lyman alpha photons and ionizing photons escape together along the line of sight. Here is just a cartoon to show you how this thing should work. And there are other objects like that. So these are two important things. The first is that this is a very compact object. I will show in a second that might be a star cluster, massive star cluster. And second point is that it was able to perforate the medium and leak ionizing photons into the intergalactic medium. This is relevant for reionization. This is another plot that is summarizing the things for this knot A. This is the surface density of stellar mass as a function of magnification, okay, for two different IMF, top heavy red, saltpeter blue. This is the stellar mass, okay, and this is the effective radius as a function of magnification. Now, we are working on the model of this lens, so we put a minimum magnification by using some geometrical constraint, but magnification is at least 20 or even up to 50. So if it is 50, we are talking about something with an effective radius of 5 parsec, and extremely dense. And so it's telling us that this very, very nice candidate star cluster. And actually, if we calculate the dynamical age as people are doing in LEGUS and in the local universe, where the line is thick, these objects start to be gravitationally bound. So this might be the first confirmation of a young massive cluster at cosmological distance, also leaking ionizing radiation. So I'm going to finish with two slides. This is very instructive because this is a sort of laboratory in several respects. And in this particular case, I would like to emphasize, this is the same sunburst arc where you have the knot C, B, and A. And this is knot A, for which we are claiming that this a star cluster. This size is must be revised when we will have a good model. Maybe you see it is 10 parsec or even smaller than 10 parsec. This is just an exercise for the moment. This is the less magnified version. This is observed, okay? These two are observed. So in this particular case, we can identify the star cluster. In this particular one, maybe we recognize there is a knot, but without lensing, all this stuff is this one, okay? So it is just to tell, it is telling us that what we can do when ELT will be operational, for example. An important physical quantity I would like to emphasize is the star formation rate surface density. Here is unfeasible to determine. Here maybe you can start to derive something. Here you can really determine the star formation rate surface density that is compatible with a star cluster, okay? Of course, if we put this kind of target on the focus of ELT, like Maori Mikado, for example, this is quite bright. In 30 minutes, no, 5-10 minutes, actually, we can get image with a resolution of 1 parsec per pixel. It is sort of super resolution. And of course, this is true also for other lenses. Okay, so I'm going to finish. This is my summary, and the message is that we are really unpacking, let's say, icy galaxies along cosmic epochs. We like to follow the star forming mode along cosmic time. We are still at the beginning in the identification of star clusters, but I think that we are really at the moment also with the HST we can do that. This is a question that mixes the two things, the reionization and star clusters at high redshift, that might be linked. There are some ideas and papers that claim that might be a connection with these two fields. So deep MUSE IFU plus Translency plus HST are providing interesting things, very, let's say, at the frontier that are calling for future facilities. And for the future, actually, of course, Mavis or more Mikado Harmony on this kind of superlensed objects or even moderately lensed objects will identify routinely star clusters up to redshift, up to the reionization. So I will say that LEGUS will be doable in the future with future facilities along cosmic time. And JWST, of course, will provide information for the rest frame optical that by definition is moved away from the K-band, so it's matter for JWST. So I will stop here, and thanks for your attention.
Okay, thanks. So, are there questions for Eros? Any expert, non-expert? I can start asking probably a very stupid one. Is in any of the observations you are reporting the risk of getting contaminations from AGNs?
Are you asking if we are detecting AGNs?
Yeah, I mean, can you exclude that the detections you are getting can be AGNs at any point? Is it easy to discard as a scenario?
Yeah, I would say that this is not a real contamination in the sense that it would be interesting by itself if we detect an object that is with an absolute magnitude of minus 15, and if there is an AGN there, means that the black hole would be extremely small. Mm-hmm. And again, would be another entire field of research that is very interesting for what concerns the intermediate mass black hole. So we can explore these things looking at the ionization lines we have from MUSE, and looking at the ratios and putting the diagnostic diagrams, at least at redshift below 3.5, we can address these things.
Below 3.5, okay.
Yeah.
Okay, thanks. There is a question by Emanuele.
Hi, Eros, very interesting. So I have just one question about your last conclusion. So on top of constraining the impact that globular cluster may have on the reionization, do you think this kind of observation can tell us something about how they form?
You're right. In fact, maybe I'm a bit biased, but here there is the other entire line of research regarding the formation of globular clusters. I'm not an expert about that. I know that people, and maybe also you are very interested in the identification of these objects during formation. I'm not sure what you really need to constrain models, because maybe we can detect star clusters at high redshift. This is feasible, in my opinion. Maybe statistically we can provide a good information. If we can perform some survey like JWST, there is a paper by Lucia Pozzetti about that, and maybe with statistics you can play a bit with this clustering, or if there is some golden age in the formation of these objects. For the single object, yeah, I don't know. I can tell you we can detect star clusters, gravitationally bound star clusters at some point, I'm pretty sure. And an example is this redshift 2.4. I don't know if it is a protosis here or not, for example.
Okay. So, and if instead of a single clamp, what you are seeing is the the unresolved sum of several clamps, would any of your conclusion change somehow?
So
assume that what you are seeing here is basically not a single system, but the result of many unresolved lower mass systems.
Yeah, this is another important point. We have a group of clamps at redshift 6, each one with a size that is between 13 up to 30 parsec. There are 8 of them confirmed in the MUSE deep lens field. We don't know if it is part of the main galaxy that we are missing because of dimming. So I think it's interesting because the clustering is telling us that this kind of objects might form together at some point. But yeah, I think this is important. I think the clustering signal will be another important parameter that need to be explored.
Yeah, I agree. Thanks a lot, Eros.
Then we have Cristiana.
Hi, sorry to move the discussion to the lens plane, but maybe I missed that, but with so many constraints, how well can you recover the lens mass density distribution of the cluster?
This would be a question for the guys that are doing the lens model. There is a trade-off, as far as I understand, among several parameters. The usual problem you have. But in this case, the number of constraints is so high that, it might be not so easy to reach a solution, to converge to a single solution. But yeah, for details, there is a paper in preparation for that will come out soon, I think, within 2-3 weeks.
Okay, thank you.
Okay, any more questions for Eros? Okay, if not, I think that's it for today. There are no other talks in our institution here in Bologna until next week, and we'll have next Tuesday Marchesi giving a talk here. And if there are no other announcements, let me thank the speaker again on behalf of everybody else, and we see each other next week. Ciao, ciao.
Thank you.
I'm interrupting.